X-ray generation. This tutorial is presented by Arindam Sarkar. In this tutorial, you will learn how X-rays are generated specifically for medical imaging and examine their features. We will learn about the technique used to generate X-rays. We will explore the basic features of the X-ray tube, the main component used to produce X-rays. From there, we will move on to the physics behind the generation of X-rays. And then we will investigate the various characteristics of the X-ray output, including energy spectrum and intensity, and how these can be controlled through different input parameters used for X-ray generation. Technique for X-ray generation. For generating X-rays in diagnostic X-ray exams, all use the same technique that includes thermionic emission or boiling of electrons, accelerating the emitted electrons by applying a kilovolt potential, that is kV, interaction of the accelerated electrons with a heavy metal target. X-rays are produced when the accelerated electrons interacts with a heavy metal target where the kinetic energy of the accelerated electron is converted into electromagnetic radiation. Two physical interactions contribute to X-ray generation. Bremsstrahlung or braking radiation, and characteristic radiation or peaks in energy spectrum. A device that accomplishes such a task consists of an X-ray tube that contains the electron source, an evacuated glass or metal envelope for electron acceleration, and target electrode material with high atomic number. An X-ray generator as an external energy source to generate high voltage for accelerating the electrons to high kinetic energy, and provides the power to the electron source for thermionic emission. This generator also permits control of the X-ray output through the selection of tube voltage, tube current, and exposure time. The X-ray tube and generator work in concert to create a beam of X-ray photons of well-defined intensity, penetrability, and spatial distribution. Let us now study a simplified diagram of an X-ray tube and briefly know its components and their role in generating X-rays. This simplified diagram of an X-ray tube illustrates its most essential components. The cathode is negatively charged and contains a coiled wire or filament which is heated to boil off electrons and acts as the source of electrons. The anode is positively charged and is the target of electrons. A large voltage is applied between two electrodes, the cathode and the anode, in an evacuated envelope. As electrons from the cathode travel to the anode, they are accelerated by the electrical potential difference between these electrodes and attain high kinetic energy. When electrons with high kinetic energy interacts with the target, X-rays are produced. We will next learn about the two physical interactions between accelerated electrons and the target atoms that generate X-rays. Bremsstrahlung radiation. Bremsstrahlung radiation is a type of X-ray radiation that is produced when a negatively charged electron with high kinetic energy gets in close proximity to a positively charged nucleus of the target anode. Coulombic forces attract and decelerate the approaching electron, causing a significant loss of kinetic energy and a change in the trajectory of this electron. As a result of this interaction, an X-ray photon is produced with energy equal to the kinetic energy lost by the electron. The direction of photon energy produced is perpendicular to the exit trajectory of the electron. This radiation is termed Bremsstrahlung, a German word meaning breaking radiation. Let us understand this interaction with an illustration. In this illustration, we see three incident electrons that interact with the nucleus of the target atom. Electron 1 interacts with the nucleus directly. Electron 2 interacts with the nucleus from a close distance. Electron 3 interacts with the nucleus from a distance. As the interaction distance between the incident electron and the target atom's nucleus decreases, more X-ray energy is generated. When the distance is zero, as illustrated by the incident electron 1 in the figure, all its kinetic energy is converted to produce the maximum Bremsstrahlung photon energy. Bremsstrahlung energies can range from 0 to the maximum energy deposited by the electron, specified by the applied kV. This is due to the possibility of interaction between these incident electrons and nucleus of the target atom at all possible distances. However, as the nucleus of an atom is very much smaller than its electron cloud, the probability of an incident electron passing close to the target nucleus is lower. Therefore, fewer high-energy X-ray photons and more low-energy X-ray photons are generated with Bremsstrahlung. In fact, this variation in energy is linear. Majority of the X-rays produced are from Bremsstrahlung radiation in a diagnostic medical X-ray machine. One important point to note is that this method for making X-rays is not very efficient. Most of the electrons just end up stopping in the anode without any contribution to this interaction. It is about 99% of the kinetic energy of the electrons that is deposited as heat in the target. Let us now learn about the other type of interaction, characteristics radiation. Characteristic radiation. In addition to the continuous Bremsstrahlung X-ray spectrum, discrete X-ray energy peaks are generated that is called characteristic radiation. The characteristics radiation is produced when an incident electron interacts with a shell electron of the target atom. If the kinetic energy of the incident electron exceeds the binding energy of the shell electron of the target atom, such interaction can eject an electron from its shell, creating a vacancy. An outer shell electron with less binding energy immediately transits to fill the vacancy. And a characteristic X-ray is emitted with an energy equal to the difference in the electron binding energies of the two shells. The characteristics X-ray energies depend on the elemental composition of the target material of the anode, and the presence of this radiation depends on the applied X-ray tube voltage. Unlike Bremsstrahlung, the characteristic radiation only produces X-rays of a few energies corresponding to the energy differences between the electron shells which the electron transits. This accounts for the spikes that you will see when you look at an X-ray spectrum. The characteristic radiation have a secondary contribution to the X-rays generated in a diagnostic X-ray energy spectrum. Now let us have a look at an illustration showing the characteristic radiation. Generation of a characteristic X-ray in a target atom occurs in the following sequence. 1. The incident electron interacts with the K-shell electron via a repulsive electrical force. 2. The K shell electron is removed only if the energy of the incident electron is greater than the K shell binding energy, leaving a vacancy in the K shell. 3. An electron from the adjacent L shell fills the vacancy. 4. A K-alpha characteristic X-ray photon is emitted with energy equal to the difference between the binding energies of the two shells. Let us now explore few electron transitions that produces prominent characteristic radiations. This illustration shows the atomic orbitals arranged by their bonding energy level. While discussing the possible electron transitions, we will refer to the X-ray notations of the atomic orbitals. Since the binding energy is strongest for the shell closest to the nucleus, K shell has the strongest binding energy. Also, there is slight variation in the binding energy in the orbitals in the other shells, here L having 3 orbitals and M having 5 orbitals. K-alpha series and K-beta series are characteristic X-rays produced when electrons from the L and M shells respectively fill vacancies in the K shell. K-alpha 1 and K-alpha 2 are specific spectral lines within the K-alpha emission spectrum. Specifically, K-alpha 1 results from a transition from the L3 orbital to the K1 orbital, while K-alpha 2 results from a transition from the L2 orbital to the K1 orbital. K-beta 1 is the energy released due to electron transition between the M3 and K1 orbital, while K-beta 3 is energy released due to the electron transition between the M2 and K1 orbital. K-beta 1 has a slightly higher energy than K-beta 3. Next, let us know the value of the binding energies of different orbitals to determine the resultant magnitude of the characteristic radiation produced by electron transitions. This table shows the approximate binding energy values in kilo-electron volts of 3 commonly used target elements for their 3 innermost shells, that is, K, L and M, and their corresponding orbitals. The value of the binding energy is dependent on the atomic number of the target element. The atomic number of tungsten is 74, the atomic number of molybdenum is 42, and the atomic number of rhodium is 45. Therefore, binding energy of tungsten is the highest. The binding energies of the 3 orbitals of L shells, that is, L1, L2 and L3 are shown, separated by oblique. For the M shell, the range of binding energies of 5 orbitals M1 to M5 is shown. Now, that we know that K-alpha 1 characteristics radiation is due to electron transition from L3 orbital to K1 orbital, we can easily determine the energy of the characteristic radiation produced by subtracting the binding energy values provided in the table. K-alpha 2 characteristic radiation is produced due to electron transition from L2 orbital to K1 orbital, and K-beta 1 characteristic radiation is due to transition of electrons from M3 orbital to K1 orbital. Next, let us see how the X-rays produced by the two interactions explained so far, that is, Bremsstrahlung and characteristic radiation, can be represented by an X-ray spectrum. X-ray spectrum. It would be nice and simple if all of the X-rays coming out of an X-ray tube had the same energy, a so-called monoenergetic X-ray beam, but in reality, while discussing Bremsstrahlung, we learned that X-rays coming out of the X-ray tube have different energies from 0 to maximum energy determined by the applied kV. X-ray spectrum refers to the distribution of the number of X-ray photons produced for each given energy. Please note here that the intensity of a X-ray beam is directly proportional to the number of photons in the beam. Therefore, sometimes the X-ray spectrum plotted against relative intensity instead of number of photons. The term relative intensity is used because the intensity of X-rays can vary depending on various factors such as the type of X-ray tube, the operating conditions, and the target material used. In the plot of the X-ray spectrum, its shape is contributed by three things. 1. Bremsstrahlung or breaking radiation. 2. Filtration from the target material, exit window, etc. 3. Characteristic radiation. Now let us see how the plot of the X-ray spectrum looks like with the contribution of these to radiation and including the filtration. Unfiltered Bremsstrahlung X-ray spectrum. This example shows an unfiltered Bremsstrahlung spectrum at 90 kV operational voltage. The maximal photon energy produced is 90 kV. This maximal photon energy is determined by the applied kV, here 90 kV. At low energies, more number of photons are produced. At high energies, less number of photons are produced. It is apparent from the plot that this decrease in the number of photons with an increase in energy is linear. When the incident electron directly interacts with the nucleus of the target atom, all its kinetic energy is converted to Bremsstrahlung radiation, and the maximal photon energy is produced. When the incident electron interacts with the nucleus of the target atom from a close distance, moderate Bremsstrahlung radiation is produced. When the incident electron interacts with the nucleus of the target atom from a distance, low Bremsstrahlung radiation is produced. When the incident electron passes the nucleus of the target atom from a far distance, there is no interaction with the nucleus. Hence, no Bremsstrahlung radiation is produced. Now let us see how this plot of the Bremsstrahlung X-ray spectrum is affected by filtration. Filtered Bremsstrahlung X-ray spectrum. This figure shows both the unfiltered and filtered Bremsstrahlung energy distribution for a 90 kV acceleration potential difference. The unfiltered Bremsstrahlung spectrum, A, that we previously discussed, is illustrated by a straight line. In reality, the photons are filtered out as they leave the X-ray target by the glass window of the X-ray tube and by additional pre-patient filtration. This filtration more strongly filters out the low-energy photons as shown in the left portion of the figure on X-ray spectrum. The filtered spectrum, B, shows the preferential attenuation of the lowest energy X-ray photons. The vertical arrow, C, indicates the average energy of the spectrum, which is typically 1/3 to half of the maximal energy, dependent on the amount of added filtration. Now let us see how this plot of the X-ray spectrum is affected with the contribution of the characteristics radiation. The filtered spectrum of Bremsstrahlung with characteristic radiation. We can see here the effect of characteristic radiation, which adds the spikes or peaks to the X-ray spectrum. These peaks are determined by the target material used in the X-ray tube. The filtered spectrum of Bremsstrahlung and characteristic radiation from a tungsten target with a potential difference of 90 keV illustrates specific characteristic radiation energies from K-alpha and K-beta transitions. We are already aware of these specific energy values for tungsten from our earlier discussion on characteristics radiation. K-alpha 1 adds a radiation spike at 59.32 keV. K-alpha 2 adds a radiation spike at 57.98 keV. K-beta 1 adds a radiation spike at 67.24 keV. Next, we will study how changing the keV and MA affects the X-ray spectrum and exposure. Effect of change in keV and MA. The main technical parameters that can be changed when generating an X-ray exposure are the applied tube voltage, keV, and the tube current, MA. Each of these parameters change the X-ray spectrum differently. The change in keV affects both the X-ray beam energy and number of photons produced, whereas change in MA affects only the number of photons produced. The patient dose in an X-ray exposure is changed with changes in keV and MA. So it is important to consider the effect of each one when setting the exposure parameters. Now let us see how the change in keV affects the X-ray spectrum. Effect of change in keV. In this example, we can see the effect of changing the keV from 80 keV to 140 keV on the X-ray spectrum. Here we can see that the maximum photon energy is determined by the keV. The overall shape of the X-ray spectrum is changed, including number of photons produced at each energy. The spectrum does not just scale up or down. The average energy level changes. The X-ray exposure is strongly dependent on the keV. The exposure is proportional to slightly greater than square of keV. Now let us see the effect of change in MEA. Effect of change in MEA. When the MEA is changed, the relative change in number of photons produced at each energy is the same. The overall shape of the X-ray spectrum is unchanged, it is just scaled up or down. The average energy level remains unchanged. The X-ray exposure is directly or linearly dependent on the MEA. We see that the effect of the MA is more straightforward. Hence, to deliver the desired exposure, typically the keV is changed first and then the MA is used to fine-tune the exposure. Effect of exposure time, seconds. Our discussion on keV and MA would be incomplete without the mention of the exposure time. When you do an exposure with the X-ray tube, you turn on that X-ray tube to expose for a given amount of time. Exposure is linearly proportional to exposure time, keeping keV and the MA constant. Similarly, as exposure is linearly dependent on the MA. Exposure is directly proportional to seconds, that is time. Whereas the number of photons produced is determined by MA, the total number of photons produced during an exposure for a given MA is determined by the exposure time. The total number of photons produced during the exposure is determined by the product of MA, tube current and seconds, exposure time. Exposure is directly proportional to the product of MA and seconds, or MAS as it is called. Where MAS, that is milliampere second, is time integrated tube current. MAS determine the total number of photons produced within the exposure time. The commonly used exposure technique in most modern X-ray machines is two-knob technique, that is kV and MAS, instead of three-knob technique, that is kV, MA and seconds, as used in older X-ray machines. Next, we will take a closer look at how filtration affects the X-ray spectrum we learned while discussing about Bremsstrahlung. Effect of filtration. Let us now examine the effects of filtration on the X-ray spectrum by means of an illustration. The blue graph represents the unfiltered spectrum. The green graph represents the spectrum after inherent filtration. And the red graph represents the spectrum after added filtration. An inherent filter is a type of filter that is an integral part of the X-ray tube made up of the glass envelope, the insulating oil, and the metal components of the tube itself. Added filter is a filter made of a material such as aluminum or copper, of a particular thickness in mm added on the X-ray port of the X-ray tube. Thickness of this filter determines the amount of soft X-rays that are absorbed. Soft X-rays are low-energy X-rays approximately below 10 keV. These X-rays has no contribution to X-ray imaging. On the contrary, they increase the skin dose to the patient and cause scatter, reducing the image sharpness. This is the soft X-ray range. Hard X-rays. Hard X-rays used in medical imaging are X-rays with energy typically in the range of 60 to 150 keV. This is the hard X-ray range. We will first see how the inherent filter affects the X-ray spectrum. A range of soft X-rays is cut off by the inherent filter, and the range of X-rays between soft X-rays and hard X-rays gets attenuated. The average beam energy of the attenuated X-ray spectrum is indicated by the green arrow. With added filtration, the cutoff range of the soft X-rays increases. The attenuation of the X-ray range between soft X-rays and hard X-rays also increases. As a result, the average energy of the resultant X-ray spectrum, indicated by red arrow, shifts to a higher energy level. This effect is termed as beam hardening. Filtration is the process of removing low-energy photons from the X-ray beam. Filtration increases the average energy of the X-ray beam, that is, hardening the X-ray beam. Filtration removes low-energy X-rays that are not useful for imaging and can cause scatter. This helps in improving image contrast and sharpness. However, excessive filtration can also result in a substantial decrease in the total number of X-ray photon produced, which can reduce the overall image quality. Therefore, it is important to balance the amount of filtration used with the imaging requirements of the specific application. This concludes the tutorial on X-ray generation. Let's now briefly go through the key takeaways from this tutorial. Key takeaways from this tutorial. X-rays are generated by accelerating electrons from the cathode, the source of electrons, to the anode, the target of electron, where they quickly decelerate in a heavy metal target and their kinetic energy is transformed into X-rays due to interaction with the atoms of the target, namely Bremsstrahlung and characteristic radiation. The majority of the contribution to the generated X-rays are from Bremsstrahlung radiation. Characteristic radiation adds the spikes at special energies, and the filtration removes more of the low energies. The kV changes the shape of the spectrum, thus the average energy and the dose dependence goes like kV square, whereas the shape of the X-ray spectrum is not changed with MA, it is just scaled and the dose dependence is linear. Since the influence of time in an exposure is similar to that of MA, that is, linear dependency, recent exposure techniques use time-integrated MA or MAs. Thank you for watching this tutorial video on X-ray generation. I hope you found it helpful in understanding the topic we covered. If you have any questions or feedback, please feel free to leave them in the comments section below. Your suggestions will help me create more informative and useful content in the future. Thanks again for your time and attention.